Hello class, today we're going to talk about lesson 5.1, identifying linear functions. Our objectives are that we can identify linear functions and linear equations, and that we can graph linear functions that represent real-world situations and give their domain and range. Our first vocabulary alert of the day is a linear function, which just is a function whose graph is a straight line. Our first example is to identify a linear function by its graph. So we need to identify whether each graph represents a function, explain, and then if the graph does represent a function, is the function linear? So let's look at the first one. So remember, to decide if it is a function or not, we need to check that each domain value or each x value is paired with exactly one and only one range value or y value. So if we're looking at example 1a, I see or cannot see any examples of points where an x value has more than one y value. So it is a function, and for it to be a linear function, it needs to form a line. Well, a is a straight line, so we will say that a is a linear function. B, if we look at this one, I again can't see any examples where there's an x value that has more than one y value. So this is a function. However, this does not make a line. It's a parabola. It's U-shaped. So this is not a linear function. And now C. If we look at C, there is only one domain value. It's 3. There are a lot of range values that go with that value 3. So the domain 3 is paired with an unlimited amount of range values, which makes C not a function at all. So let's look at our next example. So we have a set of ordered pairs that we need to decide if it is a linear function or not. So to do that, let's first make this set of ordered pairs into a table. Alright, so we've constructed the table. Now what we're going to do is we're going to look at the increase or decrease from one term to the next in each column. So to get from 2 to 5, we can add 3. From 5 to 8, we can also add 3. And from 8 to 11, we again can add 3. So we have a constant change in our x's. Now let's look at our y's. So to get from 4 to 3, we can subtract 1. From 3 to 2, we can subtract 1. And from 2 to 1, we can again subtract 1. So, as long as we have a constant change in both of the x and the y, they don't have to be the same number. As long as every change in the x is 3, for this example, and every change in the y is -1, this satisfies a linear function. So we can say that this set of ordered pairs is a linear function. Let's look at another example that is similar to this one. Okay, so just like the last example, let's convert the set of ordered pairs into a table. Alright, so just like in the last example, we're going to see how x changes and then how y changes. So our x, from -10 to 5, we have to add 5. From -5 to 0, we have to again add 5. And from 0 to 5, we have to add 5. So that's constant. Now let's check the y's, because remember the x's and the y's have to both be constant. So to get from 10 to 4, we have to subtract 6. From 4 to 2, we subtract 2. And then from 2 to 0, we again subtract 2. This 6 right here makes it so it's not a constant change in the y's. So these points do not satisfy a linear function. Alright, time for our next vocabulary alert. We have a linear equation, which is just any equation that can be written in standard form. In standard form is written like this, where you can write any equation in the form a times x plus b times y is equal to c, where a, b, and c are all real numbers and a and b are both not 0. Now there are some conditions to standard form. Those conditions are that x and y both have exponents of 1, x and y are not being multiplied together, and x and y do not appear in denominators, exponents, or radical signs, like square roots or cubed roots. So in this table we have some examples of linear and nonlinear equations. So we have an equation written as 3 times x plus 2 times y is equal to 10. That's in standard form. That's in the form a times x plus b times y is equal to c. A, b, and c are real numbers. 3, 2, and 10 are all real numbers. And a and b are not 0. 3 and 2 are not 0. We also have y minus 2 is equal to 3x, which we can rewrite that by writing it as 3x minus y is equal to negative 2 by subtracting a y on both sides. We've also got negative y is equal to 5x. By adding y to both sides, we can write it as 5x plus y is equal to 0. Then some nonlinear equations. We have 3 times x times y plus x is equal to 1. But we are multiplying x and y right there. That makes this nonlinear. We've also got x to the third power plus y is equal to negative 1. The x has a power of 3, which makes it nonlinear. We've also got x plus 6 over y is equal to 12. Because y is in the denominator of a term, of a fraction, this is not linear. So let's look at some examples and tell whether the function is linear, and if it is, we're going to graph it. Alright, we need to decide if y equals x plus 3 is a linear function, and if it is, we're going to graph it. So to do that, we're going to start by writing it in standard form. And let's just remind ourselves that standard form is in the form ax plus by equals c, where a, b, and c are all real numbers and a and b are not 0. Okay, so we have y equals x plus 3. We need to get all the x's and the y's on one side of the equation. So what we could do is we could subtract x from both sides. What that will do is we'll zero out the x minus x. We'll be left with 3 on the right side, and we'll have y minus x on the left side. Now for this to be in standard form, the x term needs to come first. So what we can do is we can use the commutative property to switch the x and the y, but that minus in front of x needs to go with the x. So we'll end up with negative x plus y, because y is positive, is equal to 3. We've got a equals negative 1, b is equal to 1, and c is equal to 3. A, b, and c are all real numbers. A and b are not 0. X and y do not have exponents that are anything other than 1. We are not multiplying x and y with each other. And x and y do not appear in any denominators, exponents, or radical signs. So that means that this is a linear function. It's a linear equation. So now we're going to graph that. Alright, we were not given any domain values, so remember we need to pick our own. So we're going to start by making a table, and we're going to pick 5 numbers. We will use 0. We will pick 2 numbers that are less than 0, and 2 numbers that are bigger than 0. Alright, so now we're going to substitute the x values into our equation. We'll just use -2, -1, 0, 1, and 2. So -2 plus 3, that is equal to 1. So our first ordered pair is -2, 1. Now let's do the next one. -1 plus 3. That is 2. So our next ordered pair is -1, 2. Zero plus 3 is 3. So our next ordered pair is 0, 3. 1 plus 3 is 4. So our next ordered pair is 1, 4. 2 plus 3 is 5. So our next ordered pair, and the last one we're going to worry about, is 2, 5. So now we can graph these points, plot them on a coordinate plane. Alright, so let's plot each point. We've got -2, 1. So we're going to go to our origin. We'll go left 2 and up 1. We've got -1, 2. So back to the origin, left 1, up 2. Back to the origin, 0, 3. We don't have to go left or right, but we'll go up 3. And we'll go back to the origin, 1, 4. We'll go right 1, up 4. And now back to the origin, we've got 2, 5. So we'll go right 2, up 5. Now we'll connect these dots because we weren't given specific domain values. So with a straight edge, make a nice straight line. And we want to put arrows on both ends of our line. Alright, that wraps up that example. Let's check out another one. So we're going to decide if this function is linear, and if it is, we're going to graph it. We've got y is equal to x squared. Well, guess what? It looks like that the x has an exponent that's something other than 1. In fact, we have an exponent of 2. Because of that, that means this is not a linear function. So we would say that this is not linear because x has an exponent other than 1. We need to say the fact that it's not linear and then explain why it's not linear. So let's move on to our next example. In fact, before we start our last example, I want to explain something. So for all of our linear functions whose graphs are not horizontal, our domain and range are all real numbers. So if it is horizontal, our domain will stay all real numbers, but our range will just be whatever line or whatever y value the line passes through. So there are some real-world situations where we have some domain and range that has to be restricted. So let's look at our real-world career application. Sue rents a manicure station in a salon and pays the salon owner $5.50 for each manicure she gives. The amount Sue pays each day is given by the function f of x is equal to 5.50x, where x is the number of manicures. We need to graph this function and give its domain and range. So to do that, what we're going to do is start by making a table. But when we make our table, we need to think to ourselves, does it make sense that Sue would have negative amounts of manicures in a day? And could Sue make negative money in a day? No. So when we're making our table, our x, our domain column, is just going to have positive numbers and 0 because she could give 0 manicures. Alright, so if we plug in 0, 1, 2, 3, and 4, that should be plenty of points to graph. So we have 550 times 0, which is going to equal 0. So our first ordered pair is 0, 0. Then we've got 550 times 1. Well, anything times 1 is itself, so it's just 550. So our next ordered pair is 1. If she gives 1 manicure, she can make, or has to pay, $5.50. Now $5.50, she happens to have 2 customers, she'll have to pay that twice. $5.50 times 2, that's $11. So our next ordered pair is 2, 11. $5.50. If she has 3 customers, she'll need to pay some value, where we take $5.50 times 3. That's going to be $16.50. So our next ordered pair is 3, $16.50. One more to go. $5.50 times 4, if she happens to have 4 customers, that's going to give us $22. So our last ordered pair will be 4.22. Alright, now we're going to graph this. Alright, so let's graph those ordered pairs. So we have 1 point at our origin. We've got 1 point when we spend or have 1 customer. We pay $5.50, so we need to go just a little bit above that 5 mark. 2.11, so we go over to 2 and we go just a little bit above the 10 mark. 3.16.50, so we go over to 3 up to 15 and a little bit above to get the 16.50. 4.22, and then our final point, 4.22. So we're going to go over to 4 and then up just a little higher than 20. And now we're going to connect the points, but we're going to do this line kind of lighter than the dots, because our individual points are our actual solutions. The line we're about to draw is just to show that this can keep going. Alright, we're done with lesson 5.1 on identifying linear functions. So for the rest of tonight, I would like you to do the Your Turn problems on your guided note packets. See you later.